Good morning, YouTube. In this video, I want to discuss the spreadsheet I've been using to track the 18650 cells I've been recovering for my Powerwall project. Much of the inspiration for this has come from Paul Kennett's channel, where he has a number of videos showing the analysis he's done on his battery data. I'll put a link to one of those excellent videos here and in the video description. I've added a few things to my spreadsheet that I've found very useful, so I'll mainly focus on those aspects. First off, my recovery process is to open up the laptop pack, then remove the cells, keeping the pairs intact. The Lenovo packs I started with are a 3S 2P configuration, meaning 3 pair of cells in series. If there's interest, I can post videos on my processing techniques for the Lenovo and Dell packs I've mainly used thus far. I assign each pair of cells a unique ID number for tracking purposes. And I'll show how this is used when we select cells to build up a new pack in the next video. Then I measure the initial cell voltages and record that and the laptop brand in the spreadsheet. I've noticed that pairs of cells from one battery pack often have similar voltages. You can see here all 397, these were all 372, here's some that were 366. Next, I charge each pair of cells to 4.1 volts on a battery charger. I chose 4.1 volts for a few reasons. First, my target voltage will be 4 volts per cell, and 4.1 was the closest common voltage on my 3 chargers. Secondly, at 4.1, the cell capacity is 10 to 15% lower than at 4.2, so cells charge and discharge that much faster. And finally, since some of my chargers tend to overshoot the termination voltage, a bit over 4.1 is less stress on the cells than a bit over 4.2. One downside of 4.1 volt testing is that I need to make sure the cells are charged to no more than 4.1 volts before discharge testing. At the beginning, I didn't think about this and thought I could save the initial charging step since some of my cells were over 4.1 volts. But this meant that some of my discharge test numbers were higher than they would have been from 4.1 volts. I didn't want to go back and retest all those cells, so I left the data as is and tried to be more diligent later on. I also had some Dell batteries down here, and these were 3S3P packs. So I pulled the triple cells out and cut off one cell from each. And initially, I took 2 of those singles and then joined them back together into a new pair and added that into the test, as you can see, where I have 4 pairs. I typically found cells out of the same pack were quite similar, so I think this was a reasonable thing to do. You can see pretty similar voltage, pretty similar resistance, pretty similar capacity. However, I was left with 1 single cell per pack, and I later decided to keep all the single cells separate for later testing. I'll go into what I plan to do with the single cells I have in a later video. After the cells rested for a few weeks, I then recorded the cell voltages in this column. Again, I initially thought all these cells would be starting at 4.100 volts. But that wasn't the case, so these numbers are not very reliable. So next I did an internal resistance test and then a discharge capacity test from 4.1 down to 3 volts on each pair of cells, and that data was recorded in these 2 columns. And my capacity numbers will again be lower than if I tested at 4.2 volts, and these are numbers for pairs of cells. A few simple things you can do with the spreadsheet data is to click on a column and you can see, for instance here, the initial voltage, and down at the bottom that's my average initial voltage, just about 3.7 volts. And if I click on my internal resistance, this is milli-ohms. My average internal resistance was just about 86 milli-ohms. And my average capacity was 3620. Over here on the side, I set up a histogram of cell capacities, and I split those into 100 milliamp hour bins. And my thinking here is that with 150 pairs of cells tested, this should be a fairly typical distribution of capacities. That is, if I were to test another 150 pairs next year, I should see a similar distribution. From this, I see I can probably use 3,300 to 3,500 milliamp hours as my low threshold for building the 20P or 20 parallel groups out of. And if I sort on capacity, I can see how these cells stack up. Since my battery holders are set up for 10 pairs of cells, if I make 10 groups of 10 pairs, I'll need 100 pairs of cells total. So if we come down here, 101 is my 100th cell, and we can see that that 100th pair, the capacity is approximately 3,500 milliamp hours, which matches up with the histogram quite nicely. So my initial sorting technique is kind of like dealing out cards. I take the top 10 pairs and stick one into each group or pack in sequence. And then I add that data to my spreadsheet. I have a battery pack column, and then I have a position in that battery pack. Then if I take the next 10 pair of cells, so I start down here, and I assign the first one to group 2 through 10, and then I put the last of that second group of 10 into pack number 1. This repeats until the 10th group of 10 pairs is allocated to pack 10, and then 1 through 9. To check how well this sort works, here's a pivot table that sums up the capacities of each of the battery packs. So I have pack 1, pack 2, pack 3. I have those all down here. And to make it easier to see, I've copied those numbers up here for the totals. The maximum is the 39,841, the minimum 39,550, average 39,642, and 291 milliamp hours difference, or less than 1% divergence. So I think this will be a good starting point. So the next step is to test these packs out and see what the results are. So stay tuned for the next video where we'll use this spreadsheet to build up a 20P battery pack and put that into the power shelf for testing. If you have any questions about my spreadsheet, feel free to ask in the comment section below. And if you haven't already done so, subscribe to the channel, be notified when that video is posted. And as always, thanks for watching.